thinking about isosceles and equilateral triangles. We start going back about what isosceles and equilateral triangles. What was the isosceles triangle? No. What are isosceles triangles? Yes, sir. What's that?
Guys, it has to do with the size. It has to do with the size.
We did this a long time ago. You guys have all seen this before as well.
Oh, there was like one long side and two short sides.
Oh.
I think
How many? That's equilateral. Isosceles, boy oh boy. Isosceles triangle has two congruent sides. Wow! This is something that they teach like 3rd, 4th grade, guys. This is I know, but I didn't teach you how to add either, so it's things that you guys kind of have to remember little bits and pieces here. So when you have an isosceles triangle, it basically means that you've got two sides that are congruent within that triangle. Now, you guys are all saying, oh, they have to have acute, obtuse angles and blah, blah, blah. You could have an isosceles right triangle. You can have an isosceles triangle that are acute angles. You can have an isosceles triangle that has one obtuse angle. That does not matter at all. What happens here is that you've got these two sides that are congruent, and when you have your when you have the two sides that are congruent, those two sides. Why? Good morning. It's not here. When you look at these two sides, notice that the tick marks that I put on them are pointing towards what are called base angles. Those base angles then are also congruent. So an isosceles triangle has a set of sides that are congruent, and then they have a set of base angles that are congruent as well. It's always the ones that the sides are looking at, that are opposite from the sides.
Or if you think this vertex is where those two congruent sides come together, that is not a base angle. That's actually has a special name too. It's a vertex angle.
It's included, but no, it's the vertex angle. Right. And we'll get to the labeling of that here in a second. Now, does it necessarily mean that your base angles are always on the bottom? No, you can have them off to the side. If you have base angles like that, that means that those angles they look directly at the sides that would be the same. Again, what you're doing is you're looking at the sides opposite. You're going to hear that a lot, right? The whole opposite sides.
When we get to trig, you guys have to get used to looking at these diagrams, marking the diagrams, and knowing what's opposite an angle, what side is opposite an angle, what angle's opposite a side. And the reason why I love this is because this ties into our conditional statements. If I have a triangle with two congruent sides, then I'm going to have two congruent base angles. And the converse is also true.
If I have the triangle with two congruent base angles, then
I have two congruent sides.
Right.
It's beautiful.
So basically the generic straight out definition of when you're working with the isosceles triangle, it would probably be a great idea, besides closing our congruent book out because we're not using them right now, to have this in one of your squares. Excuse me. It's a really nice thing to have on there to throw, like you were just saying, your conditional statement on this, because it's true. It does not change. That's kind of the big thing when you're looking at the idea of working with isosceles triangles. Now, not only are we working with proofs on an isosceles triangle, a lot of times times we're also working with algebra. And that's because you're going to see a little more algebra stuff there too. All right. So the main idea though, the main thing is to remember that an isosceles triangle has one set of congruent sides. And those sides are always looking at the sides opposite. I'm sorry, those sides are looking at the angles opposite them. Remember, when you think about it, when you're drawing it out, think of it as you make your tick marks. The tick marks are pointing towards the angles that are congruent. Okay? Tick marks are pointing towards the angles that are congruent. The tick marks of the angles. The tick marks of the angles open up towards the sides that are opposite them. The sides that are congruent. Okay? That's how these guys work themselves through. Now, within isosceles triangles, there's also a couple other little properties there. Like Ms. Thoreau was just saying, the way that we label isosceles triangles is that if we call this, we'll go back to one here. Oops. If I say that we have isosceles triangle ABC, if that's what they tell you that you have, there is specific inference you can make right away. When you have, when they're giving you an isosceles triangle and they give you letters, the second letter is always what we call the vertex angle. It's the angle between the two sets of sides that are congruent. So what's the second letter here? B. So if I draw a picture of it, and more often than not, you'll see me just draw the standard picture like this. That means that B, angle B, is the one angle that is between the two sides. It's called the vertex angle. So that's how you would label this out, triangle ABC. So this is the vertex angle between So when you see something labeled triangle XYZ, well, it's isosceles. It means Y is the angle in the middle, angles X and Z would be the same. That's the type of inference information you can take from the statement that you can make from that. Okay? You'll see that a lot. Okay? A lot. So this is the type of thing that you would not possibly see in a diagram. You could just be given, hey, triangle ABC is isosceles with angle A is 47 degrees. What do the other angles measure? That kind of stuff. All right. Not terrible? Now, what if I said that? What if I said that angle A is 47 degrees? What else is 47? C. C has to be 47 degrees because it's opposite the other side, because those are your base angles that are congruent. Well, what does that make B then? Well, what's 47 and 47? Well, what's left over then to get to 180? What is it? Is it 96 or 86? It's 86, isn't it? So it's 94, subtract 180. We were doing, I was helping Conrad with some third grade stuff yesterday. And they were talking about rounding to the nearest 100. And one of the questions says, it said the number was 1,525. Susie said it was 1,500. The other girl said it was 1,500. Who's right? They both are. So I know that's going to get marked wrong, and I'm going to have a great time at parent-teacher conferences. There's some, I don't know which one they want to say. They're both right.
They just
But yeah, this is the kind of stuff we'll be looking at, guys. Will they throw an X value in here and make you solve a triangle using the isosceles properties and stuff like that? Yeah, absolutely. They'll do a little bit of that too. There we have that. We did this. We did that. equilateral triangle then. Correct. Now, with an equilateral triangle, equilateral means that you have equal sides. Yes, sir? I was getting into the word lateral there. So we're talking about equilateral. We're talking about triangles that have all three side lengths that are the same. And whenever you have all three side lengths that are the same, you're going to have all three angles that are the same. Okay. And that's where you get all three angles equaling the color. 60. 60. Very good. Equilateral triangles are triangles that have all three sides that are the same, and all the angles that are the same. All the angles will always be 60. Because if you start thinking about it, isn't an equilateral triangle a fancier version of an isosceles triangle? So if these two sides are the same, these two angles would have to be the same. Then if I put in, oh, by the way, this side's the same, since these two sides are the same, these two base angles have to be the same. Well, if this one has one tick mark, this one has one tick mark, means this one has to have one tick mark. So you use some properties to get yourself through that. The sum of the triangle, sum of the angles is always going to be equal to 180. Since there's three of them, that's why they will always, always, always equal 60 degrees. I'm sorry, what's that, Josh? No. I'm telling you, equilateral, you're always going to get 60. I was just showing you why that happens, because you're actually using syllogism. Yeah, syllogism. Using syllogism to work your way through substitution. So when you talk about equilateral, you've got all the sides are congruent, all the angles are congruent. So what I want you to do then is also on a square, is we're going to do the same idea. It's the same idea. If all three sides are the same, then all three angles are the same. Or if all three angles are the same, then all three sides are the same. And the angles will always equal how much? For an equilateral triangle, the angles will always, always, always be 60. Oh yeah, if sides are the same, all three sides are the same, if and only if all three angles are the same. All three angles are the same, if and only if all three sides are the same.
You guys just mathed together.
We did.
Wow.
We did it without even looking at each other.
No, I bet you are.
So, as you get into some of the weirder stuff that happens, one of the things that happens with an equilateral, one of the things that will happen with an equilateral triangle. Now, don't write this out quite yet. If we know that all of these are 60, if we know that all of those are 60, and I bisect that angle up top there, if I bisect that angle up there, what do I get? I get two 30-degree angles. Well, what happens when you bisect that angle up top, it winds up being what's called the perpendicular bisector of the side. So you get a 60-degree here, 90-degree here, and a 30-degree there. This triangle, this is what we call a 30, 60, 90 triangle, as well as what we'll get to in a little while with what's called if I have a right triangle that is isosceles. If I have an isosceles right triangle, I have a 90-degree angle here, which very good makes these both 45s. These two triangles generate, when you look at it, you've got a 30-degree angle, a 60-degree angle, 45-degree angle, and a 90-degree angle. There's only 4 angles there total, correct? Those 4 angles become the entire basis of what's called the unit circle as you get to Algebra 2. Everything that deals with trigonometry boils down, to the usage of those four angles. Yes, sir. It kind of does, because what happens here is that you get 30 degrees, 45, 60, 90, 120, 135, 150, 180, 210, was it 225, 240? Yeah, no. Whatever, 30, so yes, 240. I don't do degrees, I usually do in radians, 270, 300, 335, and 330, 360. Yes, it's 315. Yeah. I don't do this in degree measures. I'm showing you guys in degree measures because you don't know what a radian is. It is like a lot like a protractor. Basically what happens here is that this 30-degree angle is the same 30-degree angle on this side, it's just reflected. This 30-degree angle here is the same as this 30-degree angle, which was the same as this 30-degree angle. It's just been rotated over and brought down. Rotated over again, this is a 30-degree angle here. What happens then, as you go through trigonometry, using basically these four angles, you're able to do the entire, what's called unit circle, which then generates what's called a sine wave, or a cosine wave. So I'm shifted over a little bit. Everything that you guys will learn in Algebra 2 when you start talking about trigonometry is based off of an equilateral triangle and an isosceles right triangle. And there are courses upon courses upon courses that do nothing but deal with just that. So when we say that there's just this little bit about equilateral and isosceles triangles, we talk about geometry. It's just a little bit to start, because what's going to happen is that you're going to see all of this again and then some. And it really becomes the entire basis of everything that you guys will do. If you look at your calculator has those three trig buttons: sine, cosine, tangent. That all deals with these guys. And in order for us to learn how to do any of that, we started it with this. And we're not there yet. We've got a few chapters to get to it. But don't be freaked out when you see all of this stuff again in the I forget what the new textbook is. It start of second semester or something? Yeah. So we're going to see all of that again, and it's a very, very important topic for all of high school, because once you start it here, you'll see a ton of it in Algebra 2, and if you go to pre-calc, you see a ton of it in pre-calc, and so on and so on. So I thought I'd stop and tell you, why is it important that we talk about where all this comes from? Because eventually it becomes the most important thing you guys will ever do in high school math. It's a pretty good circle. Oh! Boo! That's a good one. The other thing that this textbook does. Oh wait, could we look at this and figure out what the missing side is? What is it?
No. Yeah, 15.
Is it 15?
Yeah.
Okay, very good. What this textbook does talk about, and I want to make sure I show you guys a picture of this. When you have an isosceles triangle, if you have an isosceles triangle and you bisect the vertex angle, and you bisect that segment is the perpendicular bisector of a side. Now, if I'm talking about what's called a perpendicular bisector, that means it does two things. It's perpendicular to a side and it bisects it. So this portion here, we'll just label this A, B, C, and D. So in our triangle here, I have triangle ABC is isosceles. You guys might want to write this down. Nope, I don't see a box around it. It's just a definition that shows up in the homeworks and stuff like that. ABC is isosceles. By just saying that, it tells me that B is the vertex angle. And then I can say that BD bisects angle ABC. If I know that information, whether I infer it from the diagram, which I can in this case because I've got the two little congruency tick marks at the angle B, showing that it was bisected into two smaller portions, then I can say, I know that there is a right angles at the bottom, and that segment has been cut in half. A perpendicular bisector does two things. It creates the right angles, and it cuts a segment in half. That's what it means to be a perpendicular bisector. It's just putting two things together to do one. Okay? So then we have I don't believe we're going to have to worry about any proof with that. It's something that does show up, if I'm not mistaken, with some algebra. And that's about as goofy as any of this comes. I kind of like that this textbook did that, because I don't think that this did that until later on. Yeah. That sounds all right. It took us a long time. It takes a while for us to get to that, but it's a fairly simple thing. It's not too crazy. It's not too outlandish of an idea. Just basically, if you have an isosceles triangle, and then in the vertex angle, it's a perpendicular bisector at the side. This also, yes, ma'am. No, we're not done with proofs. We're just today's a little reprieve of them. We'll go back to more of them on come Monday when we go back to doing the right triangle proof ones with the hypotenuse legs and stuff like that. So we're not done. We're almost there. More of this. It'll be all posted, and you'll be responsible for the material. Solve for X and Y, please. Well, guys, if you're not here tomorrow, everything will be posted online, worksheets, whatever. You're responsible for the materials due on Monday. Field trips, things like this don't preclude you from missing assignments, so you guys know. What's that?
It says to serve live one day. Is it like scheduled that day?
I don't know.
Yeah, it does. I like every day.
Ladies and gentlemen, we're just waiting for a prompt here. Guys. Start in a spot that makes sense. Start in a spot that makes sense. Okay? What kind of triangles do you see? There's a right triangle, there's an equilateral triangle, and what's in between? Isosceles. Okay? So if I'm looking at any of those, I know that I have a right triangle with a side length of 15. That doesn't get me anywhere though, does it? No. But if I go to the isosceles, or excuse me, the equilateral triangle, I've got a side length of 12, correct? So if I've got a 12 here, what's here? What's here? Hey, there's a tick mark. What's there? Okay, that got me there. Not bad. Take a place and go. Now, I also know that, what does that 90 degrees symbol mean in terms of degrees? Did I say 90 degree symbol? I did, yes. And what does that right angle symbol mean in terms of degrees? It's 90 degrees. Imagine. Now, how many degrees are on each one of the angles of the equilateral? 60s. So that gives me the vertex angle of the isosceles triangle to be 30. Because all three of these have to add up to be 180, so there's 30 degrees there. Now, having this being an isosceles triangle, remember, if the sides are the same, the base angles are the same. If this is 30 degrees up top, how many degrees are left for both base angles? 150. 150. So that gives you 150 degrees between these two. So if these are both x, 2x is 150, which gives you x is, so there's your angle here. Now, we still have to figure out what's left over for that entire base side. Now, one of the things that we haven't discussed, but yet we've done numerous times, is what's the big crazy theorem about right triangles? What was the big crazy theorem about right triangles? The Pythagorean theorem. The Pythagorean theorem was what? Okay. This is another one of those things that each and every single one of you guys have seen at some point in time in your life. They assume that you still kind of remember it-ish. So what winds up here is you wind up solving a two-step equation. Something squared, I'm just going to call this a squared, plus 12 squared is 15 squared. Where your 12 and the 15, well, the 12 is a leg, the 15 has to be the hypotenuse, because the hypotenuse is always across from the right angle. That's always plays the role of the C value. So using your calculator, you type in 12 squared, 15 squared. Bless you. Subtract that out, you get 81. And what's the square root of 81? 9. So what's 9 plus 12? So there's your y value. So sometimes you have to do multiple things to get to a result. This happens to be one of those times. You have to string together the fact that you put multiple parts together. Like I said before, guys, most of the geometry that we wind up doing as we go along turns into big picture style problems. More parts to them, more setups, more scenarios to make yourselves, to make it go through. Okay? Okay? Solve for x, what do? First of all, we write it out, and we figure it from there. So let's write this out. Well, let's write it out, see what we get.
Oh, wait.
So first of all, what kind of triangle is it? Isosceles. So isosceles tell you that the sides are the same, which means your base angles have to be the same. So we set them equal to each other. So we set them equal to each other, and you have the algebra then. So 7x and 5, x plus 47. So pick out the little guy. Subtract the x, subtract the 5. X is 7. Okay. Now, if x is 7, what's my angle h? Because that's the kind of thing that'll happen. They'll ask you, what is the measure of angle h? Which means you have to do multiple steps. This happens all the time in geometry when they mix in the algebra. So you would solve for your value of x, which we did. Guys, we substitute back in. We get 7 times 7 is 49. 49 and 5 is 54. Which means this has to be 54, which is 108, which makes this 72. Very good. Okay? That's the type of stuff that we wind up having to make sure that we follow through on when we're doing the algebra. Always be cautious about what exactly they're asking you guys to solve for. In this case, I think it was just solve for x, but I'm just showing you that from time to time, you'll get that extra step thrown into it. Okay? Watch your mouth.